Hey everyone, today we're going to build an LSTM autoencoder, and this encoder we're going to use to detect anomalies in heartbeat data. And the heartbeat data will be recorded using electrograms or ECGs, and the data is coming from this website, timeseriesclassification.com, and in here we have a dataset called ECG 5000. And this dataset has been collected or pre-processed and worked on and originally introduced into the Towards Never-Ending Warning from Time Series Streams paper, and I'm going to link this paper down into the tutorial's references. And actually this dataset is a 20-hour-long ECG data which is obtained from a single patient, I believe. And yep, the patient has severe congestive heart failure, and this dataset actually contains about 5,000 heartbeats that were randomly selected and annotated. And in those 5,000 heartbeats, we have 5 different classes, and each heartbeat is recorded as 140 numbers actually. We have a training set of 500 and a test set of 4,500 examples, and we're going to do something about that. And the other important thing about this dataset is that it is basically already pre-processed, and it works quite out of the box when it comes to time series data, so we will have an easier time to work with it. Another thing is that this dataset obviously contains only a single feature, so it's univariate time series data. Okay, let me show you the ECG, actually an example of an ECG right here. You can see that we have some wines, and these wines basically are measuring the output of your heart based on some electricity that is going through your heart. And as you already know, your heart is muscle actually. So when you give the heart or your muscle some kind of electricity, the heart is actually contracting. So these movements are recorded using ECGs, and it's a pretty standard procedure when you go to your family doctor, or maybe when you enter a hospital. ECGs are relatively common diagnostic tools, and we are going to have a look at how can you detect anomalies or irregularities or diseases in your heart based on ECG data, and of course using deep learning autoencoders and LSTM neural networks. Okay, so the first thing that I'm going to do is to open a brand new Google Colab notebook, and in here I'm going to check the runtime, check that we have Python 3, we have a GPU accelerator, and strictly speaking I might not need the GPU accelerator for the training, but we are going to download a pre-trained model that I've trained in the offline, let's say, and after that we're going to use this model to make some predictions. But I'll show you how the whole process of training and all the code that is associated with it. Alright, so let me first start by checking the GPU that we have. And we have P100, so this is amazing. Alright, let me move this out of the way. And the first thing that I'm going to start by downloading the data. I've uploaded the data to Google Drive, so using this you should be always able to get the data as long as the coronavirus doesn't affect at least Google servers. or Google Drive servers. And the data is contained into a zip file, which is roughly 10 megabytes. And I'm going to unzip this. Okay. And you can see that we have a lot of files in here. We have text files, TS files, we have some sort of README file, and yep, you can see that we have RFF files actually. So I'm going to use this strange format to read the data, and luckily for us, Python do have a single package which is RFF to pandas, which is actually quite old, but yeah, it still works, or it appears that it is working. And I'm going to install this package using pip. All right. So now that we have this package in here, I'm going to start by pasting in a lot of imports and matplotlib setup, as long as some random seeds. I'm going to execute this, and we are importing the RFF to pandas package. So we should be able to read the files using pandas. Okay, so the first thing that I'm going to do right now after the imports are done is that I'm going to get the PyTorch device in place. And if we have CUDA device on the machine, we are going to use basically the GPU, else we are going to use the CPU. Pretty standard stuff, I guess. And next I'm going to load the data. I'm going to open the file, the train file. I'm going to start with it. All right, the train RFF. And I'm going to use the A2P from RFF to pandas to load this file. And if we check this, you can see that we have at least we have 141 rows, and you might recall that actually a sequence has a length of 140, and the last column in here is basically the target column or the class column. You can see that we have 5 different possible values in here. So we have 140 examples from the time series data, and then we have the target at the end. So this is pretty good format, I guess. All right, let me do absolutely the same thing for the test data. And here we should have pretty much the same thing. Yep. And the target again at the end. All right, that's great. The next thing is that I'm going to concatenate or append the training and the test data, because, well, we are not strictly speaking doing classification. We are identifying anomalies, and we want as much data as possible to train on the actually the normal cases, and I'm going to talk about that in a bit. All right, so I'm going to basically concatenate the train and test data using train.append, and this should work. Yep, the same number of columns, the target at the end, and this one should contain about 5,000 examples we have in here. So this is great. Another thing that I'm going to do is to basically shuffle the rows. because I don't want any ordering in here, and you're going to see why we are going to need this later in this tutorial. All right, so we have a shuffled data frame, so now everything should be looking good. Okay, so we have 5 different classes in here, and they are basically those. I'm going to copy and paste this. Okay, so let me copy the correct format for you. We have a normal, and this is 1. All right. We have the normal class. We have premature ventricular contraction, which is an anomaly. We have RONT, actually, premature ventricular contraction. I'm not familiar with these terms. We have premature ventricular contraction, supraventricular premature or ectopic beat, and unclassified beat. And for the purposes of this tutorial, everything that is not a normal heartbeat is going to be considered an anomaly. So basically what we are going to do is that we are going to use the normal heartbeats that we have in our dataset, train an autoencoder on that, so our autoencoder will learn what a normal heartbeat is, and after that we are going to reserve some of the normal as well of the normal heartbeats in our test set, and we are going to give the autoencoder tryouts or evaluate the autoencoder using those, and we're going to evaluate it using some of the anomaly heartbeats. And we are going to see if our autoencoder is good enough to basically detect anomalies in heartbeat data. But we are going to only train it using the normal heartbeats. Okay, so let me just print out the normal class index, and this is going to be 1. And I'm going to specify the class names as normal, RONT, premature ventricular contraction, which is going to be PVC, SP, for supraventricular premature something, and unclassified beat, UB. All right. So next I'm going to rename. Let me go up here, show you the head, and this column name is kind of strange in my opinion. It's not easy to work with, so I'm going to basically rename it, and I'm going to take, let me just do this, data preprocessing steps. All right, I'm going to take the current column names. Next, I'm going to rename the last column to target, and I'm going to set the new columns as the columns for our data frame. And if I check the head of all of this, you can see that we have target as the last column. So this is great. Okay, so we did some pre-processing, and next I'm going to do some data exploration. Let's see how many examples do we have from each class. Oh, and it looks like we have a lot of imbalance actually in here. We have almost 3,000 examples from normal class, which is actually good in our case. And the rest of the classes have a lot smaller, except for the second class, which was RONT, premature ventricular contraction. Maybe that's characterized based, or maybe this is normal when you have congestive heart failure. I'm not sure about that. So let me plot this so it is a bit easier to understand what is the quas, what does the quas imbalance actually looks like. And I'm going to use Seaborn count plot. And I'm going to set at the ticks or the quas names here. And yeah, this is pretty much the picture. You can clearly see that we have a lot of normal. We have a lot of those examples are R on T, and the rest of the examples are very small amount actually. So that's pretty good actually in our case, because we are going to train our model only on these data, and we're going to basically use all of this just for testing. So this is kind of great actually. All right, so the next thing I'm going to show you is that we are going to basically have a look at the mean values of each quas, or an aggregate of all the values based on each quas that we have here. And for that, I'm going to paste in a function that I've already created, which is called plot time series quas. And in here we have well, I'm going to explain this function in a bit, but first I'm going to show you how you can use it. So I'm going to take all of the unique quases, and this is basically 1 to 5, and I'm going to use matplotlib to create some subplots. We are going to specify the number of rows to be the length of the quases divided by 3, and 3 is going to be the number of columns, and I'm going to add 1 to this, and cos equal to 3. We are going to share the y-axis here, and I'm going to specify a figure size, which is going to be, let's say, 10 to 4. Let's start with that. And next, I'm going to iterate over each quas, get the data for this quas, and plot the data for it using the plot time series quas function that I've already pasted above. So let's do this. I'm going to take the axis from the subplots in here, and I'm going to get the data by, again, I'm going to filter based on the target column. I'm going to drop the target column because we are not plotting that. And I'm going to take the mean value basically I'm going to take the mean value for each column using axis equal to 0. So this will just give us the mean values per column. And I'm going to convert this to a NumPy array. Okay. Let me just show you what this will do, and I'm going to show you this for the, let's say, normal quas that we have. Right? Sorry, I have a typo in here. This should be the df. And if we do just this, you might get not a number, so we should convert this to a string. And as I've already said, we have the mean values in here. So the shape of this should be just 140 examples, which is what we need. So these are just the mean values here. Okay, so let me continue by calling the plot function. And I'm going to pass in the axis. Then I'm going to delete the last axis because we have only 5 classes. So they are odd numbers. And finally, I'm going to call the type layout method. And let me just do this. Yeah, so this is the result. These values are actually smoothed out. We are using a rolling mean to compute the smoothed out lines, basically, but the white areas, or the areas with a bit lower opacity, indicate the one standard deviation from the mean in these values. And you can clearly see that we have a lot of variation here in the normal example. We have not so much variation in the rest of the, or in the anomaly examples. In the normal beats have pretty much this jiggly line after the 100 step, and you can clearly see that most of the anomalies are actually containing these high dips into their values. So this is actually pretty good because we might be able to build a model that captures this pattern and is unable to reproduce or reconstruct those ones, or the anomalies. So again, this is great. And let me go back to the plot time series class. We are just converting the data into a time frame. We are applying a rolling mean, and we are getting the standard deviation of this, and we are just plotting the smoothed line, and then we are plotting the few between, which are going to be the standard deviation, one standard deviation below and one standard deviation on top of the mean. And we're basically after that setting a title, which is going to be the class name, which you are seeing here. Okay, so this, at least this plot, should give you a very good intuition about what kind of patterns, different types of classes that we have, or different type of heartbeats that we have, should follow. Okay, so let's continue with the actual data pre-processing. We are basically going to create data sets that are going to be used for training, validation, and testing using the normal cases, or the normal heartbeats. And we're going to merge all of the anomalies into a single data frame and use this as a test set that we are going to detect anomalies on. So let me start. Again, we are doing some pre-processing, and let's start first with the normal heartbeats. I'm going to take just class normal. I'm going to drop the labels because we don't need those. We know that this is the normal case. And if I check this, we should have around 3K, around 3K examples with each row just a single time series data. All right, so I'm going to do the same thing for the anomalies. But this time, everything that is not class normal. And this should end up around slightly over 2K examples of anomalies. And recall that already our initial data frame is shuffled, so we actually don't need to do any shuffling here. The data is randomly reordered. And yeah, let me continue with creating a training and validation and test set using the normal data frame. For this purpose, I'm going to use the train test split from scikit-learn. And I want to reserve about 15, around 15% of the data for testing. And I'm going to split that into another 2 examples or data frames. Alright, so let me execute this, and here again I'm splitting the normal data frame into training data frame, into training data and validation data, and I'm splitting this into 15% for the validation data. Then I'm using the validation data and split that one once more. And about 66% of the data we are going to be using for the validation. And the test. Let me redo this. I'm going to split this 50-50 for the validation and test. All right, so that gives us about 100 examples for the validation. Well, that's a bit too low if I'm training on this. So yeah, I'm splitting this once more, actually. Okay, let me return this. All right, I'm happy with that. Okay, so we have around 220 examples for the test and validation, which is all right. And in the training data frame, we have 2,481 examples just for the training, which is good, I guess. All right, so next I'm going to convert all of those data frames into sequences. And those sequences are basically going to be just arrays of NumPy arrays. So each sequence is going to be a NumPy array, and the collection of those is going to be just a plain old Python list. And I'm going to convert this into floating numbers, convert to NumPy, and convert all this to a list. So I'm going to do this for train, validation, test, and anomaly. Data frames. All right, so train sequences is going to be just an array. That's a bit too large, I guess. Let me interrupt this. All right. Yeah, you can see the arrays here. And next, I'm going to convert those sequences into torch tensors. And for this purpose, I'm going to create a function called createDataset. And we are not going to use loaders or datasets from PyTorch. We are going to just convert all of this into tensors, and we are going to train our model using just a single example at a time. So the batch size will effectively be 1. Alright, so the dataset here is going to be for each sequence in sequences. I'm going to convert this into a torch tensor, and I'm going to add a dimension to the last. I'm going to add one dimension at the end. So we have time series data, which basically contains just a single feature. So if you have more features, you might use the same code again, so it's pretty generic, I guess. Next, I'm going to take the length of the sequence and the number of features that we have, and I'm going to do this using stacking all of the dataset tensors and getting their shape. The first dimension is going to be the number of sequences that we have, which we are not interested in. Then we're going to take the sequence length and the number of features. We're going to get this from the shape, of course. I'm returning the dataset, the sequence length, and the number of features as a result of this function. And this is pretty simple, actually. So the training dataset and the sequence length and the number of features, we are going to get these by calling the create dataset function. And here I'm going to pass in the train sequences, and I'm going to basically do pretty much the same thing for the validation, test, and anomaly sequences. All right. And this is going to be test normal dataset, and this one is going to be test anomaly dataset. We are going to have basically two different test datasets. All right. And now you can have a look at the train dataset, for example, and see that we have, as a first element, we have a tensor of tensors, and you can see that the unsqueeze has basically converted each feature, each data point into an array or a tensor. So you can imagine that you might have, let's say, 2 or 3 features, and you have multivariate time series data. Each feature is going to be contained on each row, so you might be able to train this in a very generic way. Okay, so next I'm going to show you how to build an LSTM autoencoder into PyTorch. So what is an autoencoder? The magical thing about the autoencoder is that it is kind of unsupervised learning. You just basically fill it in with some data. You don't have labels, as you might already guessed, because we never actually passed in the targets. We are just dropping the targets that we have in here. And the autoencoder's job is to basically learn the pattern of the data that you're going to give it. And this pattern is learned by learning how to represent the data using some lowering of the dimensionality of the data and then expanding that dimensionality. And I know that this might not make a lot of sense, but basically the autoencoder is learning a compression or a simpler version of your data and is trying to reconstruct the data by from that lower dimensionality representation of it. And this is pretty much the essence of the autoencoder. sorry, you give it in some data, and the autoencoder is using this data to basically do a compression of it or a lower dimensionality of it, and then it is trying to represent it using this lower dimensionality to expand it. And based on how well does this job, we are getting something called a reconstruction error. So this error is basically telling us how well this particular sequence of data is understood by autoencoder. So basically we're going to train on the normal heartbeats, and our autoencoder is going to understand what normal heartbeat looks like, and then we're going to pass in some heartbeats that are anomalies, and our autoencoder will not be able to reconstruct those data points or those anomalies, and then we are going to measure the reconstruction error, and when that reconstruction error is high, we are going to say, well, this might be an anomaly. So let me just continue with showing you how you can do this. So let's build an autoencoder, or more specifically LSTM autoencoder. And this autoencoder is going to be very heavily based on the implementation provided by Jonathan Shubruk. I hope I pronounced his name correctly. And this dude has a library in GitHub, which is called Secutor, or something like that, which basically provides different types of autoencoders. For recurrent or recurrences, he has a recurrent autoencoder, variational autoencoder, and some other type, stacked autoencoder. Yeah. So this dude has made a very good job on implementing recurrent autoencoder. And what I did was basically get his recurrent autoencoder and tweak it just a little bit by introducing a linear layer into the decoder class, so it's a bit more understandable, and actually it might work even better. So because whatever. So let me just copy and paste my code for the recurrent autoencoder. Okay, so the recurrent autoencoder is basically just this class, and it gets the sequence length, the number of features, and the number of parameters that we're going to use to encode the different, if I go back to this, to encode this representation of data, or the compressed version of the data. And we have encoder and decoder. So this is the autoencoder. The encoding part is this one right here, and the decoding part is this one right here. So basically we have this, and the module is very, very simple. We are just calling the encoder, encoding the data, and then using the encoded representation, we are calling the decoder, and we are basically returning the decoded version. And let me go in a bit of what the encoder does and the decoder does. Let me start with the encoder. And the encoder is again just a PyTorch module. So you can see that at least in PyTorch, you can basically use those modules as Lego blocks and combine them in different ways. So this is what we are doing right here. And the encoder is actually two separate layers of LSTMs. So this picture is representing this very well. We have two layers of RNNs, and you can see that we are initializing those using the hidden number of dimensions, the number of parameters for the compressed or representation data, and each of those has only a single layer. And then we are using the forward method to convert this into a shape that is understandable by the LSTM layers. We have a single feature, the number of elements in each sequence. We are using a batch size of 1, the sequence length, and the number of features, which is again 1. We are reshaping the data using this. Then we are passing the data through both layers of the LSTM, and then we are basically taking the number of hidden parameters or the number of units or neurons into the hidden layer, which is this one right here, and returning this into the correct shape for that one. Then into the decoder, we are passing in the result from the encoder. We are repeating the X using the sequence length and reshaping again using the input dimension, which in here is basically the input dimension is the number of hidden parameters or the number of parameters that we have. And we are again passing the data through, let me just, okay, again we have 2 LSTM layers, and this time we are actually increasing the number of units in each one. And after that we are using a dense layer as an output layer, which basically contains, in our case, 140 examples, 140 points. For each output dimension has only a single feature, so we are basically outputting a time series, univariate time series with 140 predictions. And this is pretty much the way that the autoencoder should work, at least. Alright, so let's build a model using this one. And first I'm going to pass in the sequence length, the number of features, and our model is going to contain embedding dimension or the number of parameters, that is 128. And I'm going to move the model to the GPU. Alright, let me execute this, run this. Okay, so yeah, everything should be alright. Now that we have our model, it is time to train it, and I'm going to build a function called train model, in which I'm going to pass in the model, the training dataset, the validation dataset, and the number of epochs that we want to train our model for. Alright, so I'm going to start with creating an optimizer, and here I'm going to use Adam. With a warning rate of 0.01, which is the default, actually. And I'm going to use a mean absolute error, which is L1 was in Torch. I'm going to sum the values in the errors, and I'm going to put this on the GPU. Also, I'm going to record the history on the training and validation dataset for the losses. Okay, so we have everything we need. I'm going to iterate over the I'm going to iterate for the number of epochs. I'm going to put the model into training mode and get the losses. And I'm going to follow a pretty standard format for training PyTorch model. First, I'm going to iterate over each sequences into the training dataset. I'm going to zero the gradients because we don't want to accumulate those. Next, I'm going to put the sequence to the GPU. And get a prediction from our model. I'm going then to measure the error for this prediction. Apply the back propagation by propagating the error or the loss. And ask our optimizer to do the optimization step. Finally, I'm going to record the loss by adding it to the training losses. And this is pretty much everything that we need to do into the training dataset, on the training dataset. After the epoch is complete or the model is trained using the training dataset, I'm going to evaluate on the validation dataset. I'm going to put in the model into model eval mode. And I would request from PyTorch to not record any gradients for this block of code using the context in Python. I'm going to basically do the same thing as we did here. I'm going to record the loss, which I could copy from here, of course. And I'm going to store the loss into the validation losses array. Okay, so we have our training losses, our validation losses, and then I'm going to basically compute the loss on the training and the validation data for this epoch. I'm going to record that to the into the history and print the results. Okay, so we have all of the information recorded into the history, and finally for this epoch I'm going to print the results. Alright, after we trained our model for the number of epochs, I'm going to return the model into evaluation mode and return the history itself. Alright, just the indentation, and this should pretty much be it. Okay, so let me continue with actually training the model and calling the function. And I'm going to train for 150 epochs. And I'm not actually going to run this, but I'm going to show you the log from my training. So this is pretty much exactly the same code. You can see that we are training here for 150 epochs, and the validation error is getting very low at around epoch 100, and we are further making some improvements until we obtain a validation loss of 9.6, and you can see that our model is, at least it looks like that it is not overfitting, which is always a good thing, but then again the normal patterns might be very, very similar. So yeah, and this is a chart from the training process. You can see that at some point the loss got really large at around the 65 epoch, and then the loss became smaller and smaller after that. So this is what the training process looks like. Okay, let me continue with the tutorial. Luckily for us, I've basically stored the trained model into Google Drive again, and I'm going to download the model so we can continue without going through the training process. And yeah, let me load the model. After the model is downloaded, you can see that we have a model.pointer or checkpoint, and I'm going to load this file. After the model is loaded, I'm going to put it onto the GPU. Sorry, torch.load. Okay. So we have the model in here, and let's actually choose a threshold, and the threshold is going to be based on the reconstruction errors, and based on this reconstruction error threshold we are going to decide whether or not a heartbeat is anomaly or it is a normal heartbeat. I'm going to build a function called predict, which accepts a model in a dataset. And here I'm going to record the predictions and the losses. I'm going to use the same loss function, L1 loss. I'm going to put that onto the GPU again. And I'm going to pretty much do the same non-recording of the gradients, put the model into evaluation mode just in case, iterate over each sequence and put it onto the GPU, make a prediction, calculate the loss, and append the prediction and the loss to our results. And I'm going to return the predictions and the losses that we got in here. Okay, so let's use this predict function to make some predictions, and I'm going to record the losses on the trained dataset. So in a real world scenario, you might only have the normal cases, and you might not know what you don't know. So you might want to detect anomalies, but you have only the normal cases in your dataset. So you can basically use those to monitor the losses that you have and make a plot of the losses. and basically do a plot like this one. So you can see that the majority of the reconstruction errors or the loss that you have is below, like, let's say 25 or something like that. So we have probably more than 95% of the distribution or the density of this distribution is below 25, and we are going to choose that as our threshold. Let's say threshold of, let's say, 26. Okay, so based on this threshold, we are going to take an example to input the example time series data into our autoencoder, and we are basically going to record the threshold, and if the threshold is above and if the loss is above this threshold, we are going to classify the heartbeat as anomaly. Otherwise, we are going to classify it as normal. And of course, in a real world situation, you might want to caution on the error side. Let's say you might want to get this threshold to be a bit lower, because you might want to have some normal cases that are reported as anomalies. So in this case, the nurse or the staff might have a quick glance at the ECG and decide that, yeah, that's a false alarm or a false positive. But in the other case, you might not want to left any anomalies undetected, because if you don't detect an anomaly, your patient might have a fatal outcome. So let's continue with the evaluation of our dataset, of our model. And let's create some predictions based on the normal heartbeats. Let's see how our model is performing on these. And we are going to take the predictions, take their losses, and predict on the test dataset that our model hasn't seen. And this will be the test normal dataset. I'm going to basically create exactly the same plot as this one. And you can see that on the test dataset, we have some examples that have a reconstruction error or loss that is higher than 26, but still majority of the examples are below the threshold, and this is a good thing. Let me calculate the number of correct predictions here, and this is going to be the sum of all losses that are below or equal to the threshold. And I'm going to print out their number. This is going to be correct out of the length of the test normal dataset. Excuse me. Okay, so we have 215 out of 219, which is very good. And for the anomalies, I'm going to basically do the same thing here. Right here, I'm going to create a new subset because I want to have exactly the same number of anomalies. And I'm going to just take the first 219 examples in here and recall that our dataset was originally shuffled, so taking just the first n examples shouldn't include only, let's say, POV examples from the anomalies, and we will actually preserve the real distribution. So just the first length of test normal data set. And I'm going to basically redo this. I'm going to input the anomaly dataset here and do the chart again. And again, you can see that the vast majority of anomalies are after 25 or 6. At least this is what it looks like from this one. All right, and I'll get the counting code basically. And I would like to get all of the examples that are above the threshold. And we have 215 out of 219, which is exactly the same number. And we can basically play around with the threshold. We can basically be more on the error side and let's say like 22. Execute all of this. And you can see now that in the normal case we have slightly more errors, but in the anomaly case we are performing much better. So choosing this threshold in a way that is very precautious, you can play around and get most of the anomalies based on the threshold. So this is actually a practical problem, and it depends on the domain in which you are going to do some anomaly detection. So this threshold is, choosing the threshold is really important, and it's primarily a business level decision. Okay, so the last thing that I'm going to show you is basically some reconstructed examples along with their predictions. Some reconstructed examples or predictions along with the real data. And I'm going to show you some anomalies and some normal examples of those. So let's look at some examples. And here I'm going to paste, no, let me just write this out for you. I'm going to define a function plot prediction, which accepts a data set or a time series data, the model, the title of this chart, and an axis on which we're going to draw the prediction. The first thing that I'm going to do is to basically do the prediction on the data. And I'm going to pass in just an array of single data point that we have. Then I'm going to plot the data. I'm going to plot the prediction. We have only a single time series. I'm going to set the title. And I'm going to record the was into the title. And I'm going to round this at 2 decimal points. And I'm going to show the legend for this chart. Okay, so we have pretty much the same setup as before. We are going to need to create some subplots. I'm going to do this on 2 rows, 6 columns, basically the first row is going to be 6 examples from the normal heartbeats, and then on the next row I'm going to plot 6 examples from the anomalies, so you can have a visual comparison between the two. And we are going to share the x-axis, share the y-axis, and the figure size is going to be, let's say, 16 by 6. We'll try this out. And then I'm going to iterate over 6 examples from the normal and the anomalies dataset. I'm going to plot the prediction. Say that this is normal one. And the axis is going to be, from the first row, the height element. I'm going to do the same thing for the anomaly. Sorry, this should be normal. And I would request a tight layout here. All right. Yep, I made a mistake in here. So this is a bit too white. Let me return this. Okay, I guess that we can plot. Yeah, let me stick with this. I'll increase the height. That's a bit too much. All right, I'm happy with this. I'm going to do some unzooming. And yeah, on the first row, again, only normal. On the second, only anomalies. So you can see that the normal are very well reconstructed. We have a lot of wall errors in here. And you might say that the normals are following just the same pattern, but you might have a look at some examples like this and see that actually the patterns can be quite different, which is great in the regard that our model has done a very good job on understanding the time series data for the normal cases. And when you look at the second row, you can clearly see that our model is performing very bad on reconstructing the time series data. So this is amazing actually in our case, because the loss is high and we can pretty confidently say that these heartbeats are anomalies. So, I mean, like, this chart sums pretty much the work of our model, and I think it's performing very well, at least on this data. And if I hadn't made any errors on creating the data sets, it looks like our model is doing amazing job actually. All right. So in summary, we did make an LSTM autoencoder that is using ECG data to detect anomalies in heartbeats, and we created this LSTM autoencoder and trained it using only normal heartbeats, and then we picked a threshold based on the losses of our model, or reconstruction losses of our autoencoder, and based on that we are basically creating a classifier which tells us is this heartbeat normal or is this heartbeat an anomaly. And you can play around with the threshold based on the errors that you want to make and be more conservative or more aggressive maybe depending on the staff that you have or the patient that you have, and use basically this autoencoder to detect heart failure or some heart anomalies. So if you like this video, please share, like, subscribe. I'm going to link the source code and to the complete tutorial for this one into the description, and I'll see you guys in the next one. Thanks for watching.